Hi, my name is Molly Vick, and this is my Physics 2212 Lab 5 about magnetic braking with Faraday. Here is the overview for my lab. First, I will give an introduction including the lab setup, fundamental principles, and lab procedure. Next, I will go over my experimental data including observations, checkpoint questions, my GlowScript code, and computational model. Third, I will go over my results by talking about the interpretation, questions, and answering the what-if questions, followed by a conclusion. Here is a more detailed introduction to the lab. For the lab overview, we are looking to explore the interaction between the falling magnet and the tube of aluminum foil. The purpose of the lab is to apply and use Faraday's law with it acting on a falling magnet. The expected results are that resistivity and holes will have an effect on the falling magnet's speed. The system is the falling magnet and the surroundings is everything else. Here are the key principles used in the lab. To start, we had the Biot-Savart law, Faraday's law, Lenz's law, Newton's second law, Ohm's law, and the magnetic dipole equation and the magnetic force equation. We will use these in different parts of the lab today. For the lab procedure and to locate the magnetometer, first we mark the north pole of the magnet. Second, we hold the tube vertically. Third, we position the tube in frame of the phone camera. And fourth, we drop the magnet. The average time over 5 intervals was 1.243 seconds. Experimental data and measurements. The aluminum foil measurements of the length, width, inner and outer radius, and resistivity is listed right here, and the bar magnet's mass is 0.024 kilograms, and mu from the lab 3 is 2.136 amps. For the checkpoint questions, we can't use a ferrous tuber because the ferrous tube can be induced, and that would skew the results. So what happens to the magnet? How does this compare to the magnet falling in free space? Because the aluminum foil in the fields, the magnet falls a bit slower than it does if it were falling in free space. So now we're going to look at some of my GlowScript code. For step 1, we entered in the experiment data and we found earlier for the aluminum foil tube and the bar magnet. For step 2, this is the code I came up with to calculate the magnetic field of the bar magnet from the equations we listed before. For step 3, we calculated the magnetic flux. Here is the equation we came up with to find this in our code. For step 4, we found the current in the ring, and for step 5 and 6, we found the magnetic field at each ring. Step 7 asks us to calculate the net force on the magnet. The F net equals the magnetic force plus the gravitational force. And in step 8, we wrote the code to update the magnet's velocity and position using Newton's second law. So now we'll look at the computational model. These are the results from our GlowScript code, and we'll discuss these more in the discussion. But on the right, you can see that the force at one point, one force was greater than the other force for about a full second. And on the right of the graph, you can see that the forces end up balancing out. So for the first question, it asks us which color corresponds to the clockwise and counterclockwise current. We found that blue represented the clockwise and red represented the counterclockwise. And to answer the second question, when you flip the magnet around, the magnetic force is flipped as well. Continuing on with interpreting the simulation, how does the total time in tube of your real-world system compare to that of the computational system? How might this be made more accurate? So the computational model could be made more accurate by increasing the number of rings that are used to model the tube. And there wasn't that much variation in my model. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? As seen in the graph earlier, at one point, one force was greater than the other for about a second, and after this you can see the forces balancing each other out. So now we'll look at the what-if questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of this change? As the resistivity decreased, the current would drastically increase, which means the magnet would take a lot longer to fall as the braking force caused by Faraday's law would increase. So the second question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Holes and slots would disrupt the current flow. This then just disrupts the magnetic force and causes the braking force to decrease. Ultimately, this causes the magnet to fall faster. So, in conclusion, resistivity would affect the falling speed of the magnet as we expected. Holes and slots would also affect the speed of the falling magnet. Thank you so much for watching my video, and I hope you have a great day.